So I was just thinking, what is an agent? What do I know about it? I don't know what it is. But some places I've run into the concept in the last few years. One is kind of like a social thing that's increasingly in the circles that I find myself in, this like kind of rationality, less wrongy, AI safety sphere that I'm now in, where people are just like, did you know you can do things? And they call that being agentic. And then actually the first place where I really was confronted with the term was a few years ago, before I was really thinking about neural networks that much. I was still very much in neuroscience, spending most of my time running experiments on rats. And I just tagged along to a kind of rationality workshop that I was not invited to. And I met Alexander, who many of you know, and he was just like, why are you here? What are you doing? And I was like, I do rat stuff. And he started asking me questions, and I showed him some video of the rats doing a task. And he was like, oh my God, you're studying actual agents. There's a bunch of like MIRI Agent Foundation people there, and he like ran over to them. He was like, this guy studies actual agents. And I find that very funny because it's not a concept that I used very much in my work. And I thought about it more, and it didn't actually help very much. I was confused. I was like, apparently this is something they care about, but it doesn't seem to get me personally very far. So what are some things that I actually feel like I understand? I understand what a neuron is. I understand what a banana is. And I should say that you could look at this list and be like, well, Adam, if you were more sophisticated, if you knew more philosophy, if you knew more physics, you'd realize that I actually don't know what a banana is, because atoms are real, or maybe nothing's real. Yeah.
Sorry, are we talking about like the yellow fruit or something? Okay.
Yeah. Do you feel like you know what a banana is?
Yeah.
See, you know.
I didn't know what a banana was in this context. I thought it was some acronym.
It may be a rat nearby as well.
But this is like my personal list. These are things that I feel like I understand. This is about me. So I feel like I know what eigenvectors are. Maybe I know a little bit about what a tensor product is. Actually, I don't know what that is, but I feel like people around me know, so I'm going to count that. I know what dynamical systems are, and I know what neural firings are. And so what I'd like to do is I'd like to try to build up from the list of things I know, and try to get some purchase on things that I don't know. This is like, in general, what it means for me to like kind of begin to understand something. So some things I don't know what they are selves and goals and wanting, even things like cognitive symbols, which are so kind of core to kind of what it feels like our intelligence is made up of. Happiness, sadness, agency. These are things that I don't know. I can build like a hand-wavy kind of story that connects kind of the things that I know to these things, but it doesn't have enough concreteness for me. And so I'd like to build up. And of course, people say we are agents. And AI systems may or may not be agents, people argue. But things that I know that we are made up is a bunch of neurons firing in a network, and I know that AI systems also are made up of a bunch of nodes interacting with each other, which is kind of a nice analogy. Maybe it matters that we have a body and some sensors, although question marks. Yeah. And again, the types of things that we say we have, but I don't know how to connect to things like neural firing, and that AI systems may or may not have, or may have soon, or in the future, things like agency and desires and wants and minds and deceptive abilities and the ability to lie. So can we build up from that list of the things that I know about to the things that I don't? And you might look at kind of everything I've been saying and be like, well, this is like, you're just saying you're confused, and maybe this is like some kind of learned helplessness, and like, don't you obviously know that we have minds and cognitive symbols? Okay, actually, I don't think it's like a learned helplessness thing. I do have like a pretty optimistic, positive vision for the future. I think we can kind of connect these levels, and I think there's a opportunity that we have that we didn't previously have before the modern instantiation of AI systems, where we can actually leverage those systems as experimental and theoretical objects in order to get a clearer understanding of what they mean, even in us, and of course also in those systems. I will end the talk by pointing out that if you share that optimistic thing for the scientific project of understanding, then it also implies some very serious concerns about the safety of these things. But for the moment, focus on kind of the positive, optimistic scientific affordance that I'm going to argue we have. So let's just start
You
with.
didn't say anything about the neurons to agents, or did you and I missed that?
I'm saying I have a vision that we
Oh,
can
okay, that's-
start from
sorry,
kind of
that's-
groups of neurons interacting and kind
Get to
of
agents.
ground an understanding of agents and a lot of those other kind of lofty cognitive things in terms of neurons and their interactions in a way that we haven't been able to do up to now with like normal neuroscience. So let's just start with what it means for a neural network to have a model of the world in kind of a simple form. So probably many of you know about this already, but just to go through it very quickly. Actually, I want to frame this a little differently than we usually do. So there's a lake out there. What's that lake? That lake is a dynamical system. It has internal states, and through time it kind of evolves. And okay, there's a lake. It has a fish in it, has lots of atoms and molecules. I see a trail right there. And then there's us. What are we? We're another dynamical system. We are mostly just an eye looking at this thing and a brain. But we're also another dynamical system. So here's a dynamical system, here's another dynamical system. This lake, in going through its states, its physical states, which I will call latent states for a reason hopefully will be clear in a second. It goes through its states, and then we see photons that kind of bounce off of the lake and come into our eye and cause certain states of the retina. And those states of the retina are kind of what our brains have access to. They don't directly have access to the states of the lake. And in that sense, the physical states of the lake are latent, right? That dynamical system has these latent states and this internal updating that we only get to see kind of this different vocabulary. And then let's also posit just for the moment that the only thing we are trying to do, that our brains are trying to do, is just predict the next retinal state. So like, think of this as like the lake is, from our perspective, kind of talking in the language of retinal states, and we're getting this sequence, and we're trying to predict the next thing. So what can we say about kind of the internal structure, how to think about the internal structure of such a predictor? That is made up of a bunch of neurons interacting, that is trying to do this task. So just to put that in very simple form,
It's a cool down for a second.
If it's any consolation, it happened before. Yeah, it's not personal.
I thought you weren't paying attention.
This time the power didn't go off though.
Yeah, that's
Oh,
probably.
just like the room.
I'm just trying to move it every so often. Anyway, you guys know about this. So, instead of a complicated lake with dynamical systems, we'll have kind of a simple HMM with 3 states, which will have some internal dynamics between these latent states. Whatever, there's a bunch of arrows. And then it emits, based on its what state it's in, it emits a certain vocabulary, let's say zeros and ones and twos. And then we're going to take the sequence of zeros, ones, and twos, behind it there.
It'll fade in.
Okay, cool.
You really late to see.
Yeah. it'll take the sequence of zero. We're going to take the sequence of zeros, ones, and twos. We're going to feed it into a transformer. We're going to train the transformer to predict the next 0, 1, or 2 in that sequence. This is kind of cool how it's feeding in. And then from computational mechanics, we have a prediction as to kind of what, in principle, a predictor kind of looking at emissions from some dynamical systems that's doing latent state updating, what it fundamentally needs to represent in order to do that prediction well. And the answer to that is what it needs to represent is belief distributions over the latent states of that dynamical system it's seeing predictions from. And those latent states are, in this simple case at least, probability distributions. Sorry, the belief states over the latent states are probability distributions of those latent states. So the set of all the kind of beliefs have a certain geometry, which we actually find in the activation space of these neural networks trying to do next token prediction. So that's all well and good. It's cool that we have a theory, we have experiments that go along with it, that can kind of push on the theory. That's all very well and good. So this is like, first, I'm not saying this is like the total answer to what a world model is or anything like that. But there's something very concrete here in that every single part of this story, I feel like I know what's going on. And you can, maybe you'd argue with using the word world model here or whatever, but at least I know what's going on. Okay, but agency, or an agent feels more like at least it should be something active, right? It's not just kind of an eye and a brain looking at the world. It should be interacting with the world. So let's try to push forward on that. And that's not even to talk about things like wants and desires and goals, right? So just one small little step. The thing that we know about, or that I feel like we know about so far in the story, is we know about predicting. And okay, so how does this relate to kind of interacting? Well, what if we just start with predicting the outputs of transducers interacting? So Alec mentioned transducers, I'm sure other people did before I arrived. Even that, I think, is too far of a jump. So before we get to there, let's start with, instead of a predictor, because we know what predictors are, so I want to force predictors into the story. Instead of a predictor predicting kind of the output observations of two interacting transducers, let's start with just something simpler, which is having kind of a trivial case of interacting transducers. So you have two transducers interacting, but instead of the interactions being there, let's make them trivial. So they're not actually interacting, they're both just kind of normal generative processes that are generating tokens. So what is this like? You have multiple dynamical systems that have their latent state dynamics, they might have whatever structure. They're each kind of speaking in a language of zeros, ones, and twos, and maybe threes, I don't know. And what we're going to now train a predictor to do is predict a composite system, where composite here means you take kind of out of the Cartesian product of the two sequences. And what should we expect a predictor to do? Well, if you take kind of the naive story from our original thing, the generator for this kind of producted space has, if this has 3 and this has 4 latent states, then the minimal, and these are both minimal, then the minimal generator for the producted space stochastic process has 12 states, just the multiply the number of states, and so your beliefs live in an 11 simplex. So that's the naive thing. So we can run an experiment, and what I'm doing here is, there's an image missing here, but what I'm doing here is I'm training a transformer not on 2 such processes running in parallel, but on 5. And the way that the math works out is that if the product space is like over 400 dimensional simplex, the beliefs live in a 400 plus dimensional simplex. What we actually find is when we look at the dimensionality of the activations in this system, we find that it really only fills up like 10 dimensions. So what's going on here? Well, each of the processes, each of the independent components each require two dimensions to represent their belief states, and the transformer just naturally factors it into that space. So it's able to save an enormous amount of space by factoring kind of the generative process of the data into these 5 independent components. And then of course at the end, it needs to kind of combine and do the product, which it can do, apparently.
Sorry, can or can't?
Can.
Okay.
There's an image somewhere. Okay. Here's the image. So these are on the top here, are kind of the ground truth beliefs for those 5 processes. And of course, I'll show you in a second on the next thing I'll show you. In the product space, if you took kind of the emissions for each of these things and you producted all the emissions and then treated that as a stochastic process, and then tried to think about beliefs for that stochastic process, these would be 400 or so dimensional, and but what the transformer actually does is kind of factor into 5 2D spaces, where it's representing, in this case, pretty lossy versions, but still, this kind of fundamentally 5 separate 2D things. Yes?
Are they lossy just because it's hard to get, it's hard to train effectively on the high dimensional data, or is there something about having this product embedding that's reducing the accuracy of the belief
Yeah, I'm
states?
not exactly sure what makes it. So clearly, in many cases of these factor processes, just in my experience so far, something about the producting, like it's doing a pretty hard thing, right? It's being trained on a 430 something token vocabulary. It needs to like kind of magically figure out that it's being created by these 5 independent things, which each have a particular geometry. So it's a pretty non-trivial task.
Trying to discover that subspace that they live in, where the data is most correlated.
Yeah, so I'll show you in a second what the geometry kind of actually looks like to give an intuition. But it is clearly a harder task than just a normal thing. That being said, I think it's true that if you just give it 5 things that all look the same, and you still do the added product thing, it becomes easier. So exactly what is easy or hard, I don't know. But even with like kind of, it's having difficulty finding like the precise shape, but it clearly finds 5 2D things. And you see that actually by looking at kind of, I'll miss it by a second. These cumulative variance explained curves. Anyway, if you look at the dimensionality over training, it kind of starts high, so it like takes up kind of random initialization. You just kind of put sequences in, and you look at the activations. It takes up a lot of space, obviously, because you're just randomly placing these contexts into the activation space. Let's say something around 40 dimensions out of 64. And then what happens is it very quickly goes down to like 4, and then it goes up again to 10. And what you can actually see is that what it's doing is it's first learning the 4 dimensions that are associated with 2 of those components, and then it's slowly learning the rest of the 6. And so there's this interesting dynamic. Some factors are easier to learn than others, and we can see that all play out. It's a pretty cool and intriguing story. And then,
There it is.
yeah. Where's the, oh, one second. So what is the actual geometry of this? Is this like geometry of factorization going on here? So there's, let's just go to a simpler case so that we can think clearly about what exactly this geometry of factorization looks like. Imagine we have 2 processes, 2 factors, where each of them are 2-state hidden Markov models. So beliefs for each of them independently live on a line, right? Probability distributions over 2 things just live on a line. Once you have your P of this state, you already know this one's 1 minus P. So you have a line here and a line here. And then if you kind of Cartesian product these two things, you get a square. All your beliefs live in a square. That's what I'm showing here. But if instead you kind of product at the level of the generator, you get a four-dimensional generator, which has beliefs in 3D. But if you do the math out and you look at, so all the beliefs live in a 3 simplex, so like a 3D triangle.
Tetrahedron.
Thank you. But the way it turns out that the square actually embeds, so all the beliefs in this producted space between the two 1D things actually embed itself in this 3D tetrahedron in the following way. So what's going on here? You have a super high dimensional, well, this is one more dimension in this case, but in general, because you're multiplying, and you're multiplying many things, you get this exponential increase in the space where your high dimensional unfactored beliefs, producted beliefs live. And it's like you're taking this simple square and you're kind of deforming it in this way that is it has some fancy term in algebraic geometry called the Segre embedding that I don't know too much about. But there's like a geometric statement here, right? To understand that the world is factorizable is exactly to make them move from like this kind of high dimensional, super nonlinear thing to this kind of linear, simple shape. So there's also a kind of a geometric understanding about what it means to kind of to be a predictor and to understand that the world that you're observing from is made up of different components.
Can I say a comment on this?
Yeah.
So even though you have this low dimensional manifold in the joint space, the linear span of all those beliefs, it fully spans the large space.
Yeah.
So it's kind of the same thing that like if you did do the joint representation, you really would expect kind of all activations to be adding up, but it's really doing the factorization to identify specifically that submanifold.
Yeah, there's something interesting that like you get this picture where like to understand the factorization, it's like you're doing this pretty complicated nonlinear dimensionality reduction on kind of the producted space.
Okay, questions about that. It looks like a minimal surface.
Yeah.
It's like a still bubble.
Yeah.
Yeah.
Basic surface and information geometry, this one here.
But
Specific.
I always forget what the color means. What does the color mean in this picture?
I'm just coloring this space so that each point has a unique color, so we
I
can
see.
keep track of.
But then when you show the other, the usual sort of simplex.
The same thing.
Same thing. The colors aren't meaningful other than just identifying with some other.
That's right.
Okay.
Yeah. It's just so like.
So how do you think about the fuzziness? So you have these nice movies and you show snapshots, so the object is not quite indistinct and then sort of sharpen up into a nice Sierpinski gasket simplex. Go back to the other side. Oh, yeah, there. Oh, one more. Back. There.
Yeah.
So the lower row, notice how they're fuzzy.
Yeah.
So the way I think about this is actually the system is mostly starting to learn what we would call macroscopic variables, and that's going to be the embedding simplex that we eventually see. But the fuzziness is coming from dealing with the microspace, which is the 400-dimensional space. So one of the interesting questions is, how do you describe that contraction? And the way I think about it is actually dissipation from the macro variables you're seeing down to the microstates in the 400-dimensional space. So we should be able to talk about entropy production, that sort of thing, dissipation for this picture, as a monitor of how it's organizing into the lower dimensional space.
Yeah, when I see this picture, I think very much of your work with Sarah's work with you about exactly kind of coarse graining on this. And,
Well, it's a slightly different picture. It's like I have the macro thing here and then hidden, but that's embedded in 400 dimensions, and we're projecting down into this lower dimensional space, and that's all. Those are all
I see.
fluctuations.
Yeah.
All fluctuations, and it's kind of annealing and finally down this cooler, more symmetric picture in the lower dimensions.
Yeah.
So there's this kind of rate of contraction, and I'm saying you should think about this macro space, low dimension, embedded in the micro space, extremely high dimensional.
Yeah.
With some kind of dissipation.
Yeah. That seems like a
is
cool
a
direction.
proxy for convergence to the low dimensional space.
Yeah, that seems like a very cool direction. Okay, so that was all cool, but what does it have to do with transducers?
Everything.
Okay. So what if we now take the outputs of two transducers interacting and then train another neural network to predict their collective output? So what we had previously is we had these two generative or multiple generative processes, 5 generative processes that were kind of independently not interacting at all, and then like we see the Cartesian product of their outputs and try to predict. But now let's have those things interact. Okay, again, the naive story was belief over the outer product space, although already maybe we know that that's not true from our previous results. So, results there. So what I have here are 5 processes. There's 3 MES3 processes and 2 of these quantum ones. They're all in a chain in this particular case. And
When you say they're all in a chain, like one is feeding to the next
one is feeding
in a
to the
feed
next.
forward network.
So what does that mean in terms of kind of latent states and dynamical systems and stuff? I think of it this way. We have kind of a parent, so to speak. We have a first latent generator that's kind of going and it's emitting tokens. And then as a function of the emitted token of the first one, the second one has a certain dynamics. And as a function of the output of that second one, the third one has a certain latent dynamics, and so on and so forth in a chain. So there's 5 kind of latent factors here, each with their own kind of internal dynamics and emission probabilities based on those internal dynamics and the state. But the specifics of the way that the dynamics go for each latent thing is a function of the outputs of the previous one. And so there's these interdependencies between the factors, they're no longer independent. And we see very much a similar story as what we had previously. It finds the 10-dimensional representation. Things again are quite messy, so like obviously this thing is a pretty noisy version, or no, I don't know if noisy is the right word. It's a pretty something version of this thing, but it does live in 2D. Thermalized version of that. And because of these conditional dependencies, even with MES3, you get like some pretty cool looking ground truth shapes. The ground truth is on the left and what's actually in the residual stream and the activations of the transformers on the right. So things line up pretty well. Here are the quantum things. So it seems that transformers can even find these factors when there are interdependencies between the factors. So again, just to say it again, transformers naturally factor out beliefs over each factor / transducer, maybe some extremely proto type of an agent. Okay, that was like a lot of gymnastics. What does it all mean? So I think one thing that I find cool, interesting, is that a predictor trained on something that starts to feel like a proto agent like this, interacting, naturally factors its kind of understanding of the thing into subspaces corresponding to each of the transducers. So that starts to give you a picture that an agent is too strong of a word here, I admit, but I'm going with it. Stay with me. So an agent is this gives a story that's like, an agent is a separable factor in a predictor's internal structure when predicting certain types of data. What types of data? Data where there is some kind of useful factorization of the space to save a lot of dimensions. So what happens when the predictor is itself part of that interactive agentic loop? Well, maybe you start to get something like a factor that corresponds to a model of the self. But also this is more general than just agents. It's, I think, a more general story about cognitive variables and symbols. And agents and selves might be kind of one particular type that has certain qualitative and hopefully maybe even quantitative signatures.
Sorry, can you say a little more directly? You just gave us examples of pictures. Where's this emergence of possible self? When you look at those graphics.
So we have not done any experiments that I would point to and say self.
Yeah.
So this is I think the thing I want to say is that the thing I find so exciting about this is that we have not just kind of the theoretical side of things, but because we have these experimental tools, that we can probe and understand and kind of see this factorization
Right.
kind of directly.
So you're seeing this.
I think these are for sure factors, right? Okay, let me try to get this out.
Okay.
So what's going on in these experiments? You're observing composite outputs from multiple factors, even interacting factors. That's great. And the predictor factors its beliefs into subspaces corresponding to each of those factors. That's amazing. Now, what happens if the predictor is itself part of that interactive loop? I have not run any experiments on that. I don't think any of us have, but one can now conceive of actually running an experiment with that.
Just back up. I'm
Yeah, yeah.
interested in the previous sentence. The
Yeah.
predictor is part of. Say that again.
The-
More explicitly. How's that different than your chain?
It might not be that different from the chain, other than one of the factors in the chain is now explicitly part of the prediction test.
Okay.
So right now the predictor in these experiments is kind of like an external system that's just kind of observing
Okay.
the composite output of these interactive systems.
So how do you see that graphically? A sixth simplex you're
I don't know what's going to happen.
Oh,
I legitimately,
all right.
I don't know, but it's the thing that I find exciting about it is that I can conceive of an experimental and a theoretical kind of.
Yeah, I'm
Okay.
kind of more with it. I
Yeah,
just
yeah.
want to see a little more concretely what your intuitions are about this.
And another
Something
thing,
showing up
Yeah.
geometrically.
Yeah. Do I think it would be a sixth thing? Yeah. I mean, that's my naive thing at the moment.
just
Yeah.
another thing quickly that seems interesting about this is that for it to recognize it as a self, or like, you probably would want the predictor to get data about that process from two places. One, a new factor that affects what the overall dynamics are, that it can factor out. But secondly, maybe also having proprioception, that like, it's not just that I saw the cup being moved,
That's right.
is that I also could link that up sort of systematically with like my proprioception.
Yeah, yeah.
And then those linking up and making me notice, oh, actually there's some process here consistently
Yeah.
mapping to each
Yeah.
other.
Right.
So like, what is proprioception? So like, each of these, the lake is in some sense talking to you through retinal states, right, in this setup. And proprioception is a version of talking to yourself in a different language than what is the true internal.
You're talking to yourself, and also
yeah.
you see that the cup moved, like
Yeah,
those
yeah.
those things that are.
Yeah.
Which also means I think you can't have a sense. You would predict that you couldn't have a sense of agency if you didn't have the proprioception, because then it would just seem like some other process in the world causing stuff.
Yeah, maybe.
No, you don't well, if you're talking about proprioception in the neuroscientific term, then you don't necessarily need proprioception, right? You can just do it with vision or something else, or it might be too slow and so on.
But how do I know I am doing this rather
Because
than
it keeps on
someone-
happening that every time this...
every
this-
time I notice that I'm moving. Right.
And here this would be articulated as some additional data stream, commenting on how you're looking at the
I
five
think-
subspaces.
Yeah, I mean, you can make it another 5, or you can do an additional one. I think the main thing I would have
Because
is
I don't understand, giving a flexible answer is not helpful.
Yeah.
I want to be more specific.
Yeah,
Maybe- okay.
I don't think I have all the
Okay.
details worked out.
Oh, sure.
Yeah. Okay, so what might an agent be in this kind of setup? Maybe it's a particular type or set of factors in a predictive system.
Mhm.
Like, what's a desire? Maybe a desire is also kind of a factorization of
Mhm.
viewing another agent with a particular type of correlational structure. What exactly that type of correlational structure is, I don't know. But you do kind of get these like two kind of somewhat opposing views, although maybe they're not that opposing. There's one kind of answer to like what is an agent, which is it's kind of it's a property of the predictive system observing other agents. So it's like the thing is calling the other thing an agent or understanding it as an agent. But there's also something that is true of the data stream that makes it useful or like a good idea to call it an agent. So there's these kind of two things. One of them is like, I find it useful to call Paul an agent, and another thing is that there's actually something true about Paul that makes him an agent, and that also makes it useful. So I don't know where I stand on this dichotomy, or if it even is a dichotomy. But really, like I was saying before, the main thing I find exciting is that we can build up kind of step by step in this way to kind of ground our understanding in these quite lofty cognitive terms that really do have to do about like the types of beings we are and the types of beings we might be building as a society in these AI systems, and really kind of grounded in things that at least I feel like I understand. And yeah, this opportunity is afforded to us by the existence of modern neural nets, which are engineerable up to our desired level of complexity, which are amenable to theory in a way that I think, at the moment at least, neuroscience is not, and which are made up of nodes interacting and can carry out actually interesting cognitive behavior. So that's like a pretty optimistic scientific vision, right? Like, I actually think we can understand intelligence and agency and cognitive symbols, like for real. And that's all pretty optimistic, but I just want to point out, if we can really use these machines as experimental tools and theoretical tools to make progress, understanding things like intelligence and agency, then it really does suggest that intelligence and agency are engineerable, creatable, and potentially coming. And I think, like, I wanna just kind of argue that we should really kind of take intelligence and agency seriously. And what does that mean to me? It's like to notice how special these things are in kind of our world and our life. And if you really do believe that these modern AI systems can give us some intellectual purchase on these subjects, to notice what it means to actually build systems and to have systems working not with kind of the biological constraints and kind of the long evolutionary and societal kind of history, where in some sort of equilibrium we've been able to kind of move around, like we make changes to our intelligence, society can kind of have at least a little bit of time to kind of deal with those changes and to come to some quasi-equilibrium, maybe, arguably. To really kind of build these systems, and potentially soon, and to take intelligence and agency seriously, means that it's like a legitimate concern. So I think, like, if you buy at least a little bit into the optimistic vision of the scientific project that I think is afforded to us, I actually think you can't do that and not admit that there's a real concern on the other side about safety. And I think, just another note, this is like hot personal take, but it's very easy to brush off these systems as kind of not really intelligent, or not really agentic, or not really having a mind. This is something I hear quite often. But when I hear many people kind of make these claims, and I kind of push them to give me what is it about humans that makes you so sure that we have these? Like, what are these things in us? And when you push them to say something that, again, I feel like I know what it actually means, that'll be something like, well, it can make a plan and carry it out. Well, LLMs already can make plans and carry them out. I think that's, I don't know, for me, I'm like extremely confident that this is true, and I find it like obvious, more or less, that this already exists. So I think, like, a lot of times I'll hear things like, well, they don't really have minds, but I don't know what it means for us to have a mind, or why we're so sure that we have minds. Or if we are sure, why aren't we also sure? So there's this kind of double standard.
We are sure we have minds, we kind of define it that way. But then
Okay,
it's
sure.
maybe not an interesting definition.
Yeah, but why are we sure that they don't have minds, I guess? And a kind of a similar thing that I've seen recently is people, even just in the AI space, just be like, oh, what these systems really need are kind of some kind of symbolic logical system, because humans have that, and that's what like fundamentally makes them intelligent. And I'm just like, what is it about us that makes you think we have that? Or like, what is it about us that makes you think we have that in a way that these systems you're sure don't have?
Because your mother loved you.
Yeah. So I think there's an enormous amount of anthropomorphism going on. It's worse than anthropomorphism. It's
It's pseudo-anthropomorphism.
yeah.
It's a
that's right.
biased anthropomorph,
Yeah.
Sure.
So the positive version of this is it's an opportunity to not rest on those intuitions and to really push and make philosophical, conceptual, scientific progress on these things. Again, with the caveat that if you really believe that, there is this other side where to take intelligence and agency seriously means we need to be concerned about the whole project. And I'll end on that.